Hello guys, I'm Gopal and today I'm starting my first ever video in the education stream. So I've not choose the topic which is quite difficult. I thought I would have it up in my very first video, so I choose a bit of a topic which is easy but confuses most of the students. That's the circuit analysis using Kirchhoff's charge law and nodal analysis. First of all, I'm gonna tell you what's Kirchhoff's charge law and nodal analysis. Then I'll do a few problems, one or two problems on that, which will give you clarity. First of all, let's learn what is Kirchhoff's charge law. Now let me take a circuit. Let us take this junction O. Let us have some wires coming into it, going out. See, now we have wires A, B, C, D, E, F, G, and H. Now, Kirchhoff's charge law is always applied with respect to a junction or a node, and our node here is O. Now we can clearly understand what are coming in and what are going out. I mean the currents. We will name which are coming in and which are going out respectively. We can clearly see by the arrows coming into this junction are A, H, D, G. These wires, through these wires, the current is coming into the junction or the node, and through the junctions to the wire, B, C, E, F, B, C, E, F. Did I miss out anything? Nothing, I think so. Through these wires, the current is going out. So we can clearly understand by the arrows, through these junctions the current is coming in, and through these it's going out. So now Kirchhoff's charge law is nothing but it tells us the most basic thing of circuit analysis. It tells us that the amount of current coming into a node or a junction is equal to the amount of current going out of a node or a junction. So we can conclude that the amount of current coming into the node is always equal to the amount of current going out of the node. So this is basically Kirchhoff's charge law, and we can simply do it after understanding the statement. If you have clearly understood it, we can simply understand that the amount of current coming through AHBG is equal to the amount of current going through BCEF. Now if we name this as the current IA, IB, IC, ID, IE, IF, IG, IH, if we name those in such a manner, then we can easily conclude that amount of current coming in through these wires, that is IA plus IH plus ID plus IG, is equal to the amount of current going out through these wires, IB plus IC plus IE plus IF. This is our Kirchhoff's charge law for this particular diagram. In generalizing the point, Kirchhoff's charge law is nothing but the summation of current which is incoming is equal to the summation of the current which is outgoing. KCL, Kirchhoff's charge law. We can conclude in this manner that the sum of the current incoming is equal to the sum of the current outgoing. This is nothing but Kirchhoff's charge law. Now that you have understood Kirchhoff's charge law, let's move on to nodal analysis. Node analysis is always better when understood with a diagram than of conceptual understanding. So I will take a sum and I'll explain nodal analysis through that, and hope you understand it. Okay, now just take a second, look at the sum, read the given data, and read the question. It's a really simple sum. For some people it might look complicated, and I'll help them out definitely. Okay, let's get going now. This is a really simple sum and I'll do it real quick. And now for doing nodal analysis, you should understand that always the potential between a plate system, an isolated plate system, is constant or same. Now here this is an isolated plate system. Let me use another color. This is another isolated plate system. This is another isolated plate system. I'm sorry for using the same color. This is another isolated plate system. So the potential difference in this isolated plate systems is the same. I mean individually for each it is different for each system, but it's same in one system. So for doing nodal analysis, okay, like I said, for doing nodal analysis, you always have to consider a reference potential, and it'll be damn easy if you consider it across the battery. Now, the given potential of this battery is E, that is 110 volts. Okay, like I said, the potential difference across the battery is 110 volts. Now, let me tell you how to consider the reference voltage. For example, you have some circuit like this. This is the battery, positive terminal, negative terminal. So some circuit. Let's not worry about that. Imagine they have given the potential difference to be V. So consider the reference potential on the positive side is V1 and the negative side is V2. Make sure whatever you might consider V1 and V2, that's up to you, but it must satisfy this condition: V1 minus V2 equals to V, which is the given potential difference. You might take any value of V1 and V2, but it must satisfy the condition V1 minus V2 equals to V, which is the given potential difference. Mostly I like to take V1 as V and V2 as 0, which makes things much easier, like you will witness in the sum. Let us take the potential on the positive side as E and on the negative side as 0. So E minus 0 is E, which satisfies the condition. So now, as we have discussed already, this is an isolated plate system, so the potential across this system is the same. So it is 0 here, it is 0 here, it is 0 here, it is 0 here as well, 0 here. And in this system, it is E here, it is E here as well. And this is an isolated plate system, so we have to consider something for this. Let's take X here, and X. Because it's a plate system, it has the same potential. And let us consider Y here, Y and Y. So now, for getting the potential difference between A and B, it's nothing but Y minus 0. So we have one thing, potential difference between A and B is nothing but Y minus 0. So we need to get the value of Y. We'll solve it using the concept we learned of Kirchhoff's charge law and the nodal analysis, which I'm going to show you. Now, let us take this node and apply Kirchhoff's charge law on that node. Let us consider a current coming into this node like this from here and going out of this like this. You can clearly understand it's the positive terminal, current coming into this and going out like this. It's simple. So we know that Q equals to CV. This is the basic law, basic formula for capacitors, where Q is the current, C is the capacitance, and V is the voltage, potential difference, or whatever you might call it. Now let us apply this. Amount of incoming current is equal to amount of outgoing current. So let us take this Q1, Q2, and Q3. So Q1 equals to Q2 plus Q3. That's Kirchhoff charge law, or KCL, abbreviation KCL. So Q1 is the incoming current and Q2 and Q3 are the outgoing currents. So Q1 equals to Q2 plus Q3. That's the KCL. Now using this formula, if we take it, the capacitance of this capacitor is C1. So Q1 will be C1 into E minus X. That's the potential difference. The potential here is X. The potential here is E. So E minus X will be the potential difference across this capacitor. So Q1, the current passing through the capacitor, will be C1 into E minus X. Similarly, Q2 will be into X minus Y, because the potential here is Y, here it's X, so X minus Y. And here Q3 equals to C2. This is C2, mind you. If you get a little confused with all the notations here, just rewind a bit and see the diagram out first. Then you might want to write it down on a paper, so you can refer and get some clarity. C2 into X minus 0. The potential in this plate system is 0. So X minus 0. So now we've got Q1, Q2 and Q3. So we will put in this equation. So Q1 equals to Q2 plus Q3. See how simple things become. C1 into E minus X equals to C1 into X minus Y equals to C2 into X minus 0. So E C1 minus X C1 X C1 equals to X C1 minus Y C1. So this is not equal to, it's plus, equals to X C2. So we already, this is a given condition, C2 by C1 equals to 2. So we can conclude C2 equals to 2C1. So substituting this thing here, EC1 minus XC1 equals XC1 minus YC1 plus X into 2C1. We get this from here. C2 equals to 2C1, C2 2C1. I just substituted. Now cancel all the C1 thing out. That makes things easy. E minus X equals to X minus Y plus 2X. And if you simplify the equation, you get 4X minus Y equals to E. This is equation number 1. Now we got to solve for another equation in the same manner and get the value of Y. So I drew that diagram again for your comfort. Let us continue our problem. Now that we consider another junction, we consider this junction as seen in the previous thing. For this system, the potential is X, and for this system, the potential is Y. So now we apply KCL for this junction. So current coming in is equal to current going out. So current coming in through the second capacitor of C1 is equal to the current going out through this capacitor C2. So applying Q equals to CV and Kirchhoff charge law again, we get this, let this be Q1 again, and this be Q2. Since it's another case, we can take the notations. Q1 equals to Q2, simple. So C1 into X minus Y equals to C2 into Y minus 0. Since if you might like to rewind the video, we have taken the reference potential on this system to be 0, so it's 0 here. So it's Y here and 0, Y minus 0 in X minus Y, simple. So we know that C1 equals to 2C, C2 equals to 2C1, it was given and I did it. So C1 into X minus Y equals to 2C1 into Y. Let's cancel the C1 thing out. X minus Y equals to 2Y. Simplifying the equation, we get X equals to 3Y. If you look at the previous equation, 4X minus Y equals to E. 4X minus Y equals to E and X equals to 3Y. So on seeing this, we can easily solve the equation and get the value for Y. Let's substitute X equals to 3Y. So 4 into 3y minus 3 equals to e. So this is number 12y minus y equals to e, which implies 11y equals to e. So y equals to e by 11. If you have seen the sum, e equals to 110 volts. So 110 by 11, this goes into 10 times. So we have got that y equals to 10 volts. As I previously described, potential difference between a and b is nothing but y minus 0, because the potential here is y and the potential here is 0. So y minus 0, as we got y equals to 10 volts, y minus 0 equals to 10 minus 0 equals to 10 volts. So the potential difference between a and b boils down to 10 volts. It's as simple as that. Okay, now I'll come up with another pretty easy sum which might look haphazardous in first look, because it sounds like it's really tough, but it's pretty simple. If you think it's really tough, then I'll make it pretty simple for you. This is nothing but, first let me explain the question. This is nothing but an infinity series, a series which continuously exists, which you might have heard in your regular curriculum. This is an infinity series with capacitors aligned like this, C1, C2, C1, C2, C1, C2, and the battery has potential difference of V, and the potential difference between 1 and 2 is V2, 3 and 4 is V by 1 and 2 is V by 2, sorry, 3 and 4 is V by 4, and 5 and 6 is V by 8, and so on. So the question is, they have asked me to find the ratio of C1 to C2, that is C1 by C2. It is really simple. Let us do the exact same thing which we did for the previous sum. Let us take isolated plate systems. So I've highlighted the isolated plate systems, and you know about taking the reference voltage potential, right? We will take it as V here and 0 here. So 0 here, 0 here. And in the previous case, we considered the potential difference here to be x and here to be y, because we don't know about it. But here they have given between 1 and 2 is V by 2. So I told you, while considering reference levels, the difference should be equal to the given potential. Here it is 0. So when we take V by 2 here, V by 2 minus 0 is V by 2. So it satisfies the case. And it is V by 4 here. So V by 4 minus 0 is V by 4, so it satisfies the case again. So the potential of this plate is V by 2, and the potential of this plate system is V by 4. Now let's do the sum. Consider this junction. If you might want to try the sum on your own, please pause, go on, get the answer and check it if it's correct. Or if you want to see my explanation, then please carry on. See now. The current coming in is the current going out, like just in the previous case. So C1 into Q equals to CV, like in the previous case. C1 into here it's V by 2, V minus V by 2, V minus V by 2 equals to C1 into V by 2 minus V by 4, be careful here, V by 2 minus V by 4, okay, V by 2 minus V by 4 plus C2 into V by 2 minus 0, just like in the previous case. So now let's do it. C1 into V by 2 equals to C1 into V by 4 plus C2 into V by 2. Let's cancel all the V things out here, makes things easy. C1 by 2 minus C1 by 4, you take the LCM. 2C1 minus C1 by 4 equals to C2 by 2. Cancel this thing out. C1 equals to 2C2. So C1 by C2 equals to 2. Damn simple, right? Thanks a lot for watching, guys. If you find my video lessons helpful, please drop a like and comment your expressions and comments, whatever you want to do. And please do subscribe, which will really motivate me to take up other topics. And if you find any mistakes in my video, please feel free. I am open to suggestions. Please drop a comment about my mistake, or whatever you like about my explanation. And if you really think there's some other method which is quite easier than this method, then I'm open to suggestions again. Please do drop it in the comments, which will help you and me and lots of other fellow students as well. Thank you.